Hi students, welcome to lecture 19. Please take out periodic table and table S. Let's first discuss the alkali metals in group 1. Alkali metals in group 1 range from Li at the top here to Fr at the bottom here. And as you can see in the electron configuration, alkali metals all have one valence electron, which the atom loses to form the +1 ion. And alkali metals are the most reactive metals. Specifically, alkali metals are never found uncombined in nature. Specifically, instead, when exposed to air, they'll form oxides when exposed to oxygen in the air. And the oxide formula, or the formula for their oxides that they form, is X2O, where X is just the alkali metal. For example, the oxide of sodium or Na is Na2O. The oxide of lithium or Li is Li2O. And if you follow this pattern, obviously, the oxide of K or potassium is just K2O, so you see the pattern there. And the reason why alkali metals are most reactive is because they're so close to an octet, so they can very easily just lose their one electron, since they're so close to an octet, to attain a noble gas configuration, so they're quite reactive. As a consequence, they react very violently with air and water, as you can see sodium reacting with water here, making it very violent. And you can also compare the reactivities of alkali metals against one another, and how you do that is you'll find that reactivity increases down the group, where Li is least reactive since it's at the top, and Cs and Fr would be pretty much the most reactive since they're at the bottom. Now you may think that Fr is the most reactive, however, the reason why we don't say Fr is the most reactive commonly found metal is because Fr is less abundant and radioactive, so it disappears very readily because it's radioactive, because it decays, and there's so little of it. So more commonly we think Cs is the most reactive metal, because CS is more found abundantly. However, Fr could technically be correct, but I'll just go with CS for now, just because it's more commonly found, and therefore CS is the most reactive. The reason why reactivity increases down the group is because atomic radius increases and first ionization energy decreases down the group. So as you get further and further down the group, it takes less energy to pull off the electrons, and you're further away from the nucleus, so you feel less attraction. So it's easier to remove electrons and be metallic, as metals should be. So it's even more metallic down here as you get further from the nucleus. Finally, alkali metals are soft, shiny metals like sodium here or potassium here, as you can see. All right, next we have alkaline earth metals in group 2, which range from the top here, beryllium, all the way down here to Ra, or radium. And alkaline earth metals, as you can see by the electron configuration, all have two valence electrons, which the atom of the alkaline earth metal loses to form a +2 ion. And alkaline earth metals tend to be very reactive metals. They're obviously not as reactive as alkali metals, but they are still very reactive. Specifically, they're never uncombined in nature. Instead, when they're exposed to oxygen in the air, they will form oxides. Their oxide formula that they form when exposed to oxygen in the air is XO, where X is just the alkaline earth metal. For example, the oxide of magnesium or Mg would be MgO, the oxide of Ca or calcium would be CaO, and obviously if you follow that pattern, the oxide of strontium or SR would be SRO, just plugging into XO. And alkaline earth metals tend to be very reactive because they lose two valence electrons and they're so close to their octets to attain a noble gas configuration really quickly. As a consequence of this explanation, alkaline earth metals will react with air and water very readily. Also, some alkaline earth metals like magnesium will react very readily with hydrochloric acid. All right. Finally, alkaline earth metals are very soft, shiny metals like you see down here for Be all the way to Ba. All right. Next, let's discuss transition metals, which are in groups 3 to 12 here, as you can see here. All right, or the D block in other words. Now, transition metals are metals whose positive charges can vary. The reason for this is because they have partially filled d orbitals, so they can lose a specific number of electrons to form multiple charges like V with +2, +3, +4, and +5. And as you know, transition metals are less reactive than groups 1 and 2 because these two groups are the most reactive of all metals. Now, transition metals will tend to form very bright, colorful compounds in aqueous solution, such as cobalt, chromium here and here, nickel here, copper here, and manganese here, and even iron 3 ions when you put them in water. And the reason why they form brightly colorful compounds in aqueous solution is because the electrons in partially filled d orbitals promote easily to excited states. So they'll kind of like have that brightly colorful compound in solution. So make sure you memorize this explanation for both the Regents as well as for the SAT exam. Now, transition metals tend to be very strong, shiny metals on their own. Finally, I want you to know that transition metals often do not abide by the octet rule. As we learned in the last unit, the valence electrons of the D block elements, or the transition metals in group 3 to 12, have valence electrons in the S subshell all the time. However, for the SAT Chem, something you do need to know, this is not always the case, but you do need to know this as happening occasionally for the purposes of the SAT Chem exam, is that the transition metal can have valence electrons in the D orbitals or D subshells. All right, so make sure you know that for the SAT Chem exam. All right, next we have lanthanides and actinides, or the F block elements, which are these two rows at the bottom of the periodic table. And these are called the inner transition metals because they're sort of nested in the D block somewhere. And something you need to know for the SAT Chem exam, this is not always the case since we know that valence electrons are always in the highest subshell. But for the SAT Chem exam, I want you to know that potentially lanthanides and actinides can potentially have valence electrons in F orbitals and F subshells since they're in the F block. All right, now lanthanides also can be considered rare earth metals. The reason for that is because they're rare on Earth. And lanthanides are very shiny metals that are similar in reactivity to group 2 metals since they're so close to them. Finally, actinides tend to be very radioactive elements. Specifically, thorium, atomic number 90, to neptunium, atomic number 93, tend to be naturally radioactive elements. On the other hand, the remaining actinides from Pu all the way to the N tend to be artificially or man-made radioactive elements. Okay? So make sure you know that. Next, we have chalcogens in group 16. And chalcogens, as you can see in the electron configurations here, all have 6 valence electrons. Since they're so close to an octet, the atoms of chalcogens just have to gain 2 valence electrons, or they will gain 2 valence electrons to form negative 2 ions, as you see by the top oxidation state here. Chalcogens range from oxygen at the top here to polonium at the bottom here, atomic number 84. All right, and the compounds of these chalcogens are called chalk-forming compounds. Specifically, chalcogens, like oxides and sulfides and so on and so forth, form because the chalcogens in group 16 readily bond with the metals to form compounds, and these compounds are often known as ores in nature. Finally, stable solid chalcogens tend to be very soft and poor conductors of heat. For example, sulfur is a stable solid chalcogen, and it's very soft because you can crush into a fine powder, and it's also a very poor conductor of heat as well as electricity. All right. Next, we have halogens in group 17, which range from fluorine at the top here all the way down to acetine, atomic number 84 down here. And halogens tend to have 7 valence electrons, as you can see in the electron configuration here. So the atoms of halogens, since they're so close to octets, will gain 1 valence electron to form negative 1 ions, as you see by the top oxidation state here. And halogens are the most reactive nonmetals. Specifically, they combine by either sharing or gaining electrons, and when they react with metals, they will form something called halides. And these compounds known as halides always have the halogen in the back with the metal in the front. All right, for example, 2 examples of halides are NaCl and MgCl2, where the halogen in the halide is ClCl, and the metals in the front are Na and Mg here and here. All right, now halogens tend to be the most reactive nonmetals because they're so close to an octet. As a result of being so close to an octet, they very readily will gain 1 valence electron from a metal atom when they form an ion to attain a noble gas configuration very quickly. As a result of being the most reactive nonmetals, they react very violently with other elements. And you can also compare the halogens' reactivities against one another by seeing what happens to reactivity down the group. Specifically, reactivity decreases down the group. Since F is at the top of group 17, it's the most reactive nonmetal of all nonmetals. And as you go down the group, you'll find that reactivity decreases down the group because electronegativity decreases or attraction decreases and atomic radius increases down the group, so you get further and further from the nucleus. As a result, the nonmetal's nucleus does not attract electrons as strongly, and therefore it's not as nonmetallic. All right, I also want you to note that halogens are all diatomic elements such as F2, Br2, and also, as you see here, Cl2 and I2. All right, finally, I want you to know that halogens exist as solids, liquids, or gases, okay? Finally, we have noble gases in group 18, ranging from He at the top down here all the way to Rn at the bottom here. Now, as you can see in the configuration, noble gases all have 8 valence electrons, and they're very non-reactive elements. Let's remember why from what we reviewed earlier. They're non-reactive because they have a completely filled valence shell, and therefore they have a stable electron configuration with an octet of 8 valence electrons, therefore making them stable. The only exception to this is helium, which has 2 valence electrons to be stable, but it's still stable nonetheless. And noble gases are all monatomic or one-atom gases, as you can see here for helium, neon, argon, Kr, Xe. Finally, let's see why the reaction between alkali metal Na and halogen Cl is so violent to form NaCl or sodium chloride. The Na atom's Bohr configuration is 281, so what does it need to do to get an octet? Well, the Na atom needs to lose 1 valence electron to form the Na plus ion, giving you the Na plus ion's configuration for Bohr of 28. And then Cl atom, as you can see here, is the Bohr configuration 287, so what does it need to do to get an octet? Well, the Cl atom needs to gain 1 valence electron to form a Cl minus ion, so therefore giving you the Cl minus ion's Bohr configuration of 288. So as you can see here, the reaction between sodium and chlorine is violent because Na atoms want to each lose 1 electron, and Cl atoms each want to gain 1 electron, each to attain a stable configuration. So the Cl atom will gain 1 valence electron from the Na atom, thereby giving you the Na plus and Cl minus ion configurations, as you can see here. And as a result of their stability, they will release a lot of energy in the process of achieving a stable configuration, therefore forming the more stable compound NaCl. NaCl is more stable than either element was alone. All right, please complete your homework for tomorrow.